So today I want to talk about design of experiments and statistical process control. Before we do that, we need to talk about some basics. One thing we're going to define is error, okay? An error, in our case, we're going to define as the variation in a measurement or process. So imagine you're making a battery electrode or something that is often unavoidable. And the idea here is we need to plan for this in how we design our experiments and how you do your data analysis. First, I need to sort of define some of the statistical concepts we need. We need to understand the idea of probability distributions. And a distribution is going to be, in this case, a collection of data points representing a population. So one way to think about that is I might, I might have a population of all people on the planet. And to represent that population, I might measure something like height for, say, 1,000 of them. Okay, so I could create a distribution from those 1,000 data points that were representative if they're randomly sampled of the entire population, but they are, of course, not the entire population. So you could imagine, for example, say I was making a measurement on a line diagram, say this was like height, and I measured, some points here, and there's some people that I measured that were scattered around and that have some average value. We'll call this Y, right? And there might be some average Y, okay? I can define a probability distribution, which is going to be going from 0 to 1, right? It's the probability of finding some sample with a given value. Generally, we'll have some sort of curve, bell curve-like shape, Gaussian type shape. And if I say have 2 points, Y0, Y1, right? And I want to know that probability, I just can integrate this probability curve. Now, this is showing a probability curve for the whole population. You might indeed have discrete points. You might make a histogram with different values and count who number of people in those values. And then you can construct this curve by fitting that histogram. Because, of course, your data points are never usually every single item in the population, okay? And so if I want to know the probability of giving a value between Y0 and Y1, what do I need to do? How would I do that mathematically? Normalize. So the area under this whole curve is 1, okay? So it's a normalized probability distribution. So one way to say that, there's a probability of getting one of these points is 100%. If you randomly draw from the population, you'll get a value that lies somewhere on this curve, right? So how would I figure out what's the probability of getting one of these points? So it's just the integral. So if you think about this, you just want the probability is going to be the area under this curve, and it's already normalized. So it's going to be the fractional probability. This is going to be the integral from Y0 to Y1 times the probability distribution of the probability distribution with respect to the value Y, right? So one thing we need to do when we start talking about real is we need to distinguish between sample and population quantities. The sample is, of course, what you measure. So this sample is going to be what has been measured, N, and it's a subset of population. And the population is everything, and that's going to be big N, okay? So we can define a few things. We can define eta here. It's not the overpotential in this case. It's going to be the population mean, and it's just going to be the sum of all the values divided by the number of values. This is what you typically think about as an average, right? A mean. And then we can also define a sample average, which is the same sort of thing. You just take up all the samples you happen to measure over the number of samples you take. And, the sample mean should approach the population mean with enough sampling, right? There'll be some error because this is a true number. This, if you know everything precisely, the population mean is a number, but the sample mean is always going to have some uncertainty associated with it compared to the true population mean. One way to say this is if the hypothesis of random sampling, so there's no bias, right? There's no bias in who I'm sampling. It's like doing a poll, right? To see who's going to win the election. You need a random poll. And how do you make sure you have a random poll, a representative group, right? So, but if the hypothesis of random sampling holds, then y bar represents eta. Okay. But you have to watch out for autocorrelation effect. Think about the weather. Weather is highly correlated. If it's raining right now and I sample again in an hour, chances are it'll probably be raining again, right? So you have to make sure that you're sampling over enough time span to average out those autocorrelation effects in that case. If you're doing a poll of potential voters and you're only calling people with cell phones, now that's almost everybody, but there was a time when a lot of older people didn't have cell phones, right? So you're actually missing a substantial portion of the population, or vice versa. You're only calling people with landlines and all the young people don't have landlines. So these are things that people think about, okay? Okay, so the next thing I want to talk about is variance. What does variance mean? Okay, I might have some distribution that looks like this. It might have a mean here. And the variance tells you about the sort of location, we'll use that, of the distribution. So another way to say this is the variance describes the spread of population, how far on average the data lie from the mean. So the population variance is going to be sigma squared, and that's going to be mathematically the sum of every single point, every point compared to the mean squared over the total number of samples n. So that's for the whole population. And then I could also define for a sample, right? A sample has fewer points than the population. Define s squared equals the sum of how far each sample is from the mean squared over n minus 1. And it turns out you have to use n minus 1 here in the denominator because you lose a degree of freedom. The way to think about this in a statistical sense is you lose a degree of freedom because we're using y bar, which is an estimate of the mean instead of the true mean. And this happens to be known as Bessel's correction. You have n minus 1 degrees of freedom. We won't get into. We can define then y bar over s. Y bar, that's the mean value in the population. S is the spread, right? The variance, the sample variance. So this is essentially what we would call a signal to noise ratio. So if you're trying to make a measurement, this would be how big is the number you're trying to measure relative to the spread in all numbers that you might measure or you might try to control in a given process. So there's another thing called the standard error. You'll often see this used. So it's good to know what these are, standard error. And that's equal to the S divided by the square root of n, the number of samples. This, the standard error, and this is something that folks can get a little bit confused on. So it's an important point. If you see standard error, this is the error on the mean. So it's not necessarily the error of any given measurement. It's sort of like how well do you know the mean value that you derived from all your measurements. So it's the error on your estimation of the mean value. So error on the mean, not error on individual measurement. The standard deviation, the definition for the standard deviation, which is S, equals the square root of S squared, square root of the variance. So the population standard deviation, sigma, is the square root of the population variance. Okay, good. So the standard error is the standard deviation divided by the square root of number of samples. And then sigma over the mean, or S over y bar, this is called the coefficient of variation, or this is percent error. The error divided by the value, and then the inverse of that, which is, so let's go and now look a little bit at a Gaussian distribution. We'll talk about how this occurs in a moment. The normal distribution, we call that Gaussian, right? Or a bell curve, and it looks like this, okay? This is P of Y, the probability distribution, or you could call this the relative frequency. You'll see it plotted that way sometimes. And if we plot this, right, it's symmetric. And then I might want to think about what fraction, and this is going to be where this is the mean eta, let's go 1 sigma in either direction, okay? Okay, so this is going to be sigma. What's sigma again? Standard deviation of the population or of the sample? Population. This is going to be, if I integrate this, this is going to be 34.1%. This is going to be 34.1%. Okay, so that's how much area is under that curve. So within one standard, plus or minus one standard deviation, what's the chance if I make a random measurement, and this is my population, it's a Gaussian, what's the chance I'm going to get a measurement that's within one standard deviation of the mean? If I make a random measurement, 68.2%, right? Excellent. So now what if I go out one more standard deviation, okay? So this is going to be, we're going to call this the 2 sigma, this is sort of the next, this is another sigma, I guess I should write it that way. So the total distance would be 2 sigma. So what area is under this? It's 13.6%, okay? 13.6%. And then if I go out one more sigma, 3 sigma, another sigma here, right? Over here, there's going to be 2.1%. Okay, so if I go plus or minus 2 sigma, what fraction of the data is that going to be? Well, it's actually 95%.
95-ish.
Yeah, so that's the 95% confidence interval. Have you guys ever heard of that interval? So that's plus or minus 2 sigma. That's how that's defined. Okay, now if I go to plus or minus 3 sigma, it turns out I get 99.7% of the data of the population. So this is essentially plus or minus 3 sigma is essentially all the data lies in plus or minus 3 sigma if it's Gaussian, right? So that's one of the ways we define outliers is based on this sort of statistical framework. And so we'll look at that in a moment. So can somebody tell me why you get these sort of distributions? Why do you get a Gaussian distribution? Where does that come from? So here's a cool example. I love this example. Okay, so why are many error distributions Gaussian, normal? And so it has to do with something called the central limit theorem, which I'll show you how you can do the experiment yourself and see how it works. But we'll write it here. It has to do with the central limit theorem. Has anybody heard of this before? Okay, so random error is the result of the sum of different errors from non-correlated variables. I mean, if you think about it, you make a battery, right? And you measure the capacity of that battery. How many variables do you think go into determining the capacity of that battery? I mean, there's probably thousands and thousands of variables, right? So if enough of those variables are uncorrelated, it turns out you will get a Gaussian distribution, a random Gaussian distribution. So let's do an example. As central limit theorem says, is that when you have enough random processes that are uncorrelated with each other, you'll end up with the net result being a Gaussian. So I like this one. You guys, some of you may have seen it. Consider throwing dice. So if I have one die and it has, a 6-sided die, what happens? What's the probability distribution if I throw that dice to get 1, 2, 3, 4, 5, 6? Is it a Gaussian? So if you had a non-equal probability of getting one number over another, you'd have a loaded set of dice and you should head to Vegas and make some money, right? Figure out how to swap them in there, okay? So now, what do you think happens if we start rolling more than one dice? So I'm going to go, so here's what happens. Now here's one dice. Okay, now what happens if I roll 2 dice and I take the number? So this is basically sum over the number of dice. Okay, that's what's going to be on this axis. Okay, so there's the distribution for 1 die. Here's 2 die, right? So what happens? Well, you still have the same average, but notice how the distribution is now starting to look different. And you can do this experiment yourself. Now, if I do it with 3 die, okay, now I'm starting to see, right, what's going on here. And then 4 die, and then 10 die, right? I mean, it's starting to look like a Gaussian. That's because one dice doesn't know what the other dice is doing. And what's really cool about this, it doesn't matter what the initial probability distribution looks like. This probability distribution of one particular event or one particular variable that's affecting the overall measurement, the total sum of all the faces of the dice, you see, right? It doesn't matter what the individual probability distribution looks like. They will always tend if you add enough uncorrelated random processes, no matter what their individual probability distributions looks like, they'll always tend towards a Gaussian. I think that's super cool. Okay, so that's the central limit theorem. Any questions on that? So let's keep going now and think about how this affects our measurements and the sort of things you might do, okay? So let's go now and talk about something called statistical process control. So that's using the concepts of statistics to think about how you are monitoring, say, a production process or monitoring an experiment you're doing. Process control, okay. So the idea is if you have, imagine you have a random process, okay. In that random process, you get some Gaussian like this, okay. And we're going to define some more terms. And so we're going to define what's called the upper control limit and the lower control limit, LCL. This distance between these two is going to be 6 standard deviations from our measured, our mean, right? And the other thing we're going to define is something called the spec limits, which are going to be larger than, hopefully where our process is giving us. Like if this was the capacity of a battery you were producing, you want it to be within some limits because you're going to provide it to a supplier to put in their vehicles that needs to have a given performance, right? So we'll call this the upper system limit, upper spec limit, sorry, and the lower spec limit, okay? And it's going to be some larger, some distance from the mean that's larger, hopefully, than your control limits, which is governed by 6 standard deviations. So this, remember, is 99.97% of all your samples should fall under this. So is it possible if I make 1 million batteries that some will be, some will be outside of the control limits? Yeah, of course, but there should be few. So let's check. Spec limits determines whether you need to trash product. That's a loss of money. Control limits based on statistics. And it typically includes all the data you expect to measure. And then there's a few things we define here. But if you think about, you put your probability distribution on its side, right? And you think about all the data you're generating. Say this is a ticker, right? So say this is time down here, and you're recording points of some value. This is your measured value. So this is the capacity of your battery, right? And you're measuring, you're looking at the data coming off the production line of some parameter you're measuring. This all looks sort of like normal, right? So how do you know when there's something wrong with your process, right? So how do you know? It needs to be a statistically relevant change, or is it just a random event? And so there's a series of rules that people often use, and different companies employ these in different ways. For example, if you're looking, these are called Schuhart or Western Electric rules. People in production talk about this stuff a lot, but I just want to familiarize you guys to it. It's not something we're going to study in detail, but it's good to have the language. So if you see 1 point outside of 6 sigma, plus or minus 3 sigma, that's typically considered a failure. Even though statistically it will happen, or it will happen at times, but that's one of the rules that you would consider a failure if you see a point outside of your control limit. That's going to happen 0.03% of the time, though, via statistics. And so the rest of these are other rare events that should only happen 0.03% of the time. For example, if you get 1, 2, 3, 4, 5, 6, 7, 8, 9 points in a row on one side of the mean, right? If you calculate the probability of that happening, it's 1/2 to the 9th power. And it turns out that's about 0.03%. So it's pretty rare that should happen. So that would consider, okay, I better check my process, right? So that's a sort of a warning to you if you're, a scientist or engineer running a process. If you see things like 6 points in a row steadily increasing or decreasing, that is also rare, right? With the same sort of probability. If you see 14 points in a row alternating above and below the mean, that means there's something going on in your process that is statistically non-random. If you see 2 out of 3 points in the 3 sigma zone or beyond, so 2 points in a row in 3 sigma is very unlikely. If you see 4 out of 5 points in 2 sigma zone or beyond, 2 in the 3 sigma, 4 out of 5 in the 2 sigma, 15 points in the 1 sigma zone, either above or below the mean, 8 points on either or both sides with no points in the 1/6. So there's these various rules, okay? And so this happened to be, I think, from a Hyundai presentation. So Hyundai, uses some of these, but not all of them for their various processes. So it's just good to have an idea about what these are. The other thing people like to talk about, the process capability ratio. And that's, we're going to call that CP, or that's what it's called. And that's the upper spec limit minus the lower spec limit over 6S actual data, right? So that's a sample standard deviation, and that's the spec limit, right? So what do you want this to be, a big or a small number if you're an engineer running a production line? Right. You want your natural variance to be very small compared to what's okay, right? So bigger is better. Okay, good. So then there's this other thing called CPK, and this is the process capability index. Okay, and this is defined as the minimum, so the smaller of the two, of either the upper spec limit minus the average, or the average or mean minus the lower spec limit, divided by 3 sigma. So this has to do with how centered your distribution is. Okay, so imagine you had an upper spec limit and a lower spec limit, or actually lower spec limit, upper spec limit, and then my distribution was actually not centered, right? And it looked like that, right? Then CPK, right, would be a lot smaller than CP. So your process is sort of working well. It's giving you a tight distribution, but your distribution is in the wrong spot relative to your spec. So people talk about CP and CPK a lot when they're doing process control. And it's sort of like the difference between precision and accuracy, right? So precision is sort of how close you can get each value. Accuracy is how close it is to the actual target. Shoot all my arrows here, I'm very precise, but not very accurate, right? Okay, so that's that. Are there any questions there?